All right, very well. Can everyone see the board here? Yes, very well. So over there you have my Twitter account. It's a test to see whether you're active on Twitter. Go there and follow me. Thank you very much for your support.
I have a bank account and one
All right, so I'm gonna be trying now to entertain you for the next half an hour with some machine learning. I'm not sure about your previous knowledge about machine learning, so I'm supposing you know nothing, and I'm starting from scratch, from zero, and I'll start to build up some concepts. Again, if you don't follow what I'm saying, stop me, ask me to repeat or to clarify, okay? You have to make yes with the head, otherwise I don't know if you're listening and understanding what I'm saying. So make yes, okay. You can also do that if you're Indian, I'm fine with that too. All right, sorry about the joke. So my name is too long. Usually you can just shorten by just using the first three letters of my name. So I can go by Alf easily, right? And that's it. So let's get started. So machine learning actually in 2018 is actually called deep learning. Why is that? Because it's cooler, more or less. But it's always the same stuff for the last 30 years. But now we have better hardware, so it goes faster and we can do much more fancy things. All right. So let's start with the taxonomy of the machine learning, the learning paradigms and the algorithms. So here I'm gonna just try to give you a very brief overview about what are the things that exist over here in this field. And I don't try to be exhaustive, I just give you an introduction so far. So we have here machine learning, which can be divided in three main subcategories. The first one is called supervised learning. What is it, supervised learning? It means you have a sample, and then someone is going to tell the machine, okay, that sample is an apple, perhaps. It's a fruit, it's an apple. I provide another sample, maybe it's another fruit, that's an orange. So I provide a third example, I provide a yellow-shaped fruit, that's a banana. So supervised learning is basically providing a machine a sequence of samples, training samples, and I associate to every sample a label. And I just ask my machine to learn the correspondence between that sample and the label. So again, supervised learning, you get a sample, and then you get the feedback from the teacher, which is providing the supervision for the student to learn. Okay? Second one is going to be instead unsupervised learning. Here, the teacher is too expensive. We don't have the teacher. They just went on a strike. You have the kid with a banana, an orange, an apple, and tries to figure out things by its own, right? So you don't have anymore the teacher, which is telling you the name, perhaps in English, and you just have the samples you can play with. And you're just trying to understand the structure, the internal structure of those kind of data. But again, there are no labels provided. Finally, in this family here, we have the reinforcement learning. What is reinforcement learning? Basically, you have a sample, you provide the sample to your machine, you provide another sample, you provide another sample, you provide another sample, and then bam, at the end, you provide the label. So you have some kind of delay label, what I'm talking about. So, for example, this stuff is when you're playing, let's say, Super Mario on your Game Boy, if you're old, or maybe other games. But basically, you have to perform a sequence of actions, and like you have your agent jumping around in your video game, and only at the end you see, oh, you succeed, you pass to the next level, or you actually died at the end, so you should have changed your strategy. So these three things can be divided, these subcategories can be divided based on when the supervision is provided. Supervised learning, you have supervision, which is the label provided with the sample every time. Unsupervised, there is no supervision. And then there is the last guy where you provide some labels, basically some supervision later on. Okay, so these are the main three categories someone can think to divide machine learning in. Today we are going to be actually focusing on the first part, supervised learning, which is the easiest part. Given that we are having those samples and those labels, that's the easiest thing you can think of, just having a machine learning a mapping from those samples to the labels. Those other things on the right-hand side are going to be used for different setups, which are a bit more complicated. For example, the unsupervised learning is used when you don't have those labels, because labels usually are very expensive. They require some human knowledge, which are providing some supervision. And as I said before, the teacher costs money, they go on strike, so you don't always have the capabilities of having labels for your data. Last one instead is basically having your machinery interacting with some kind of other thing, with the environment. So for example, you can have like a supervised learning algorithm, which is maybe classifying faces, classifying cats versus dog, making some classification or regression, like trying to predict the temperature in a specific, I don't know, place of the planet, given that you know some information like how long was the sun seen in that specific point in the globe. So that's supervised learning for doing regression. And the last one, I was saying, and then the reinforcement learning can be also used for supervised algorithms, where you have this algorithm that may interact with the environment and have like feedback from users, and then you have the system that tries to improve with some feedback, which is coming, later on in the game. All right, so this is just a really brief introduction about what we may see in the next lessons. Clear so far? Yes? No? I talk a lot, I know, sorry about that. Next one. All right, so as I said before, we have in the supervised branch there, we have classification. When we try to, for example, classify oranges versus apples versus bananas, all of them are fruits, all of them belong to the same kind of family, but we'd like to distinguish between different categories. So there you have like, you cannot express those categories with like, let's say, a number. You prefer to say it's associated to a group A, group B, group C. Whereas on the regression, we try to infer a real number. For example, the temperature on a point in the globe, or maybe the location of a point on a screen. So whenever you have to end up with some values which are, scalars, which are varying, we would like to perform a regression. Classification instead tries to put things in buckets. Okay, so far good, right? All right, let's do something more cool. Next one. So machine learning, that was the initial title of the thing, but we care about deep learning. Okay, the title is wrong. So this title should be machine learning algorithms, not deep learning. So the first one over there, I call ANN, which is shortening for artificial neural net, which is going to be the main topic of the current and the following lessons. Then are there only neural networks in machine learning? No, there is a lot of other stuff which doesn't really work. But I'm going to show you just for politeness. So we have like support vector machines. We may have decision trees. We have naive Bayes. I don't know how to pronounce that word. And you have a hidden Markov model. A lot of stuff which doesn't really work as well as artificial neural network does whatever neural networks do. All right, so where is this deep learning coming from? So that guy over there splits in two parts. There are shallow networks and there are deep networks. Now I have a question for you. Since now we are playing and talking about deep neural networks and deep learning and all those very deep fancy terms, why would anyone play with shallow nets?
Easy to train.
Say again?
Easy to train.
Oh, definitely they are easy to train, but
smaller impact, easy to implement.
So the point is that you didn't have hardware, a few years ago. Only recently, let's say in the last 5 years, we have GPUs and we have enough compute in order to perform so many computations which are associated to very long neural networks. So deep neural net means very long, very massively large neural networks that can be trained only if you have enough power. And that comes available to you only if you use, like, for example, accelerations with graphic cards, GPUs. Okay, so far is it clear what I have been talking about, right? Any questions so far? Nope? All right. So,
sorry, quick question.
Yes.
Is there anything a shallow network can do that a deep network cannot do?
Yes, be fast. And it actually, it's not actually a joke. So if you are speaking about language embeddings, they use like one layer, basically, a neural net. So they do perform, I mean, shallow networks are actually used currently whenever you need to really push forward performance. You don't need that much of a modeling power, okay? So shallow networks, although they may sound like a joke, are still very commonly used and are very useful, especially in those cases where you need really fast computation and you don't need that much power for modeling some kind of data, okay? So please ask questions, even though they may sound silly, it's all good, we learn from that. Yes, please.
So you said, so why does anyone use any of the other machine learning models if the deep learning is so much better now?
So
It sounds like you said that you shouldn't use SVM or the support vector machines.
I never said so.
Oh.
I simply suggested that this works better.
Okay.
Of course.
But that's controversial.
I know, I'm joking.
Okay.
All right, the whole point is that in here, we basically, these solutions over here, they are called end-to-end. So you have some input on the left-hand side, yes, and you have some outputs. So you have your fruits on one side, and here you have your names, banana, apples, and oranges. And you just put fruits one side, and you end up with labels on the other side. You don't have to do any other thing in between. If you use these guys over here, for example, you may need to perform some kind of feature extraction, which are maybe hand engineer features. Maybe if you're looking for images, you may use hog filters and other crappy things that have been used in the past in order to extract some features from the original data. Usually when we use deep neural nets, usually the solution is said it's end-to-end. So you have just raw input, pixels of an image, or data from an audio file. So you just use whatever data you have. You don't have to use any kind of hand engineering of feature extractor in order to apply these kind of solutions. So that's why basically these kind of algorithms have been working very, very well recently, because whenever you have your system that is trying to learn those kind of feature extractor, there will be optimal feature extractor given the data you provide them, right? So someone say, okay, I'd like to extract some sounds from a speech. So maybe I would like to plot the spectrogram, so I get like time on one axis and frequencies on the other axis. So you can end up with very different ways of extracting meaningful information. When you use deep nets, usually you just provide raw data on one side and you enforce some specific output label, which could be like, as we see before, some number, scalar number for regression, or some basically categorization. So basically some buckets, basically some indication about which category a specific sound or image or any kind of input belongs to. So in short, if I try to reiterate and summarize what I said, this solution here, usually you just have the deep net, you don't know how it works, it just works. Black magic. Seriously, we don't really fully understand what's inside. That's why you have many people that are still making research here and asking for money to make research in this area, because they say, oh, we can interpret our solutions and interpretability is better than make it work. I don't think so, but up to you. If you want to make stuff work, I would say use this stuff. Then it's up to you. It's like experimental, okay? So you can try all those things, but something works, something doesn't. Yeah.
Is there a standard metric for deciding whether a network is shallow or deep?
Let's say one layer is shallow, more than one layer. No, a few layers. Let's say it depends in which domain you're talking about. For image classification, I would say everything above 5 layers is deep, less than 5 layers is shallow. If you have audio, you may have different numbers. I think it's very dependent on the kind of input you feed these networks. This is just introduction to my talk, so let's not try to focus too much on those little details. All right. Okay, so this was the introduction, and what do we do? How do we implement this stuff? For implementing this stuff, we're going to be using PyTorch. So I was planning to go through a tutorial on how to use tensors, but I think I'm gonna be skipping this part for sake of, oh no. Would you like still a tutorial on how to use PyTorch?
Yeah.
Tensors. Yes? Okay.
Yes, sir.
All right.
Unless you have something really better you think we should do. You're the expert.
Yes, I know. I'll see. All right, let me think. Okay. All right, let's then do this tutorial. All right. And show. So if you manage to install the Conda and the Jupyter things, you can follow along. If you haven't, it's fine as well, because I'm going to be showing everything here. So I am inside my repository here. I just run Jupyter notebook. Okay. So this is on my local machine. I don't have set up anything else. I run this one and I observe this one. It's black because it's cool. You don't have to have black, but my eyes are happier to see black stuff. And I go on the first tutorial, okay? Tensor tutorial. So if you haven't used before the Jupyter notebook things, you can execute things by pressing Control and then Return. Or if you'd like to execute and go to the next line, you can press Shift and Return. So if I press here Control and Return, I am highlighting this cell and I stay in that cell. If I press Shift and Return, I actually move down. Okay? So how do I get help? For example, I don't know what functions are available. So in the first line there, I imported torch. And in here, I just press Enter to edit the cell. I can go just after the SQ. I press Tab. And for example, I can see the auto-completion. For example, here you can see there is a square root. There is a square root with an underscore. There is squeeze. So anytime you don't know, you just press Tab after you type some letters in order to have some kind of auto-completion. Okay? Going to the next thing. Let's say I know something ends up in a blah tensor, but I'm not sure what's before the tensor. Can you see? Is it too small? Should I make it larger? I can make it larger if you want. All right, so in here, let's say I'd like to know all the functions that end up with tensor. So I say torch dot, I don't know, star, then tensor, question mark. If I execute this one, for example, by pressing Control and Enter, I see below all these completions. No? So, for example, we have torch.byte tensor, torch.char tensor, and so on. So anytime you can replace the unknown part with a star, and then you can figure out what are the other options. I'm here, and I'm not sure about. I'm not sure how to use this module. Okay, so this torch and then module is something, but I'm not sure how to use it. So if I press instead within these parentheses here, Shift and Tab, I'm gonna see a small overview about the help function. Okay. So if you do Shift Tab, you're gonna see, okay, base call for all neural network modules. Very nice. So I can get some information. Otherwise, I can do basically the same by typing a question mark after the name. So torch.nn.module question mark. If I execute this line here, it's gonna pop up this message below where I have the full help for a specific function. Let's say now I'd like to know more. I'd like to know the source code of something. Sweet. I just put a double question mark. I execute that one. And here I see the full source code of whatever I'm looking at. Okay? So these are very nice, handy ways of checking help, having help for anything you're doing. So you can do Shift Tab. You get the quick memo about what you're doing. You can have one question mark or two question marks. All right, that was it. Going down. So let's start here with Torch. Before we have imported Torch. What is Torch? So far for this small tutorial, Torch is going to be simply a tensorial library. What are tensors? So we're going to figure out very soon what they are. Let's write this one. So we have t equal torch.tensor 2, 3, and 4. If I execute this one, for example, pressing Shift Return, I'm going to see, oh, t is a tensor. Wow. Okay, are you here? Are you following? Are you awake? Is it boring?
No.
Oh, okay. I thought it was. All right, sorry about that. All right, so here we have created a torch tensor. What are the sizes of this tensor? I just type t.size. And here I see, oh, the sizes of this tensor are 2, 3, and 4. You can also, I press B to go below here, I create a new cell. I can do t.shape, for example, which is like very common for whoever uses NumPy, for example. If I press enter, it's going to be exactly the same as I've done before. So in this case, this tensor has size 2, 3, and 4. Means there is some memory allocated, which has some space which is space of 4 times 3, 12 times 2, 24. So there are 24 slots allocated somewhere, which are organized in a specific way. I'm going to tell you more later. So this is just a fancy way of drawing those sizes. I just use some, basic Python in order to print here that the size of this tensor is just 2 times 3 times 4. And also I show you that you can use Unicode in Python. All right, so let's see how much memory this stuff occupies. So here we have that a point in this tensor is basically a 24-dimensional vector. So if you have one tensor of size 2, 3, and 4, that tensor can be also thought as one point in a 24-dimensional space, okay? So if you think about a 2D space, a plane, 3D space, the volume, 24-dimensional space, whatever space, this tensor is just a point, okay? Over there. And overall, it has 3 subdimensions, okay? So when I press dim here, I ask how many dimensions have this guy? And in this case, it has 3 dimensions. What are the sizes of these 3 dimensions? You have seen that before. 2, 3, and 4. Okay. If you multiply 2 by 3 by 4, you get the 24 basically degrees of freedom this tensor has. So basically, again, this is like a point in 24-dimensional space. All right, so let's actually print this tensor. Is everyone following so far?
Yes.
Did I lose anyone so far?
No.
Are there questions?
No.
Okay, should I continue?
Yeah.
Thank you so much. Oh, there is a question over there.
What was the shortcut to create a new line again?
So I just press B to go below.
B.
You can press A to go above. You can automatically create one cell above or below. And this works in the notebook. I don't know the other thing they use here. All right, so I'm going to be executing. I keep executing, okay? Stop me again if you need any suggestion, okay? Is there any problem here in the first line?
Keep going.
Okay, all right, I asked. All right, so here I'm executing this T. Bam, disaster. What's happened? I don't know. Overflow when unpacking long.
It didn't happen to me.
Okay, so something happened here. Something basically was not initialized. Oh, yes?
I think you might need to change your kernel so the code has
I don't have I didn't follow the...
He's left. He has a different.
Yes, I didn't follow any instructions. I'm not sure. Yeah, I was one of... Anyhow, something happened here. I'm not sure, but I'm gonna just replace whatever happened inside those T. So whenever we are using some functions with a underscore, we're gonna be overriding the content of something. So here I put t.random underscore 10. In this case, I just override the content of that initial tensor with random numbers from 0 up to 10 excluded, okay? And basically it fills up here these 2 tables that are 3 times 4. So right now maybe you start understanding what is this tensor, right? Before we said that sizes of this tensor were 2, 3, and 4, right? And here you can see, there are 2 matrices of 3 by 4. So maybe you start getting an idea of what a tensor is, but I still haven't defined it. So right now, if I execute this line, before it was actually crashing, I had no clue what was going on. If I'm gonna be executing this line here, actually, we see that the content of t has been overwritten by the new content. Okay, right? So far, good. Okay. All right. So let's keep going. In this case, I say R equal torch tensor of t. So basically, create a new tensor from t, and then I would like to resize with underscore. So what does it mean underscore? Can you remind me? It overrides. So it does some. It changes something. Okay.
But that's a torch specific thing.
It's a torch specific thing. So in this case, R at the beginning here is going to be just a clone of T, sort of speaking, in loosely speaking. Okay, it's not a clone. It's a proper clone. It's like a copy. Let's say it's neither a copy. It's a kind of replica. I'm trying to find a different word of
Copy
T.
versus in place.
Yeah. So I'm just okay. Just forget what I'm saying. I just read what's happening here. So R is going to be generated from T, and then I resize R. Okay. So if I execute this line here, you can see that now the overall tensor that it was before, like expressed as a couple of two matrices. Now it has different size. Okay. But the content is the same.
Now it's a matrix.
All right, so now what I'm doing here, I'm saying r dot 0 underscore. Who can guess what's going to be happening?
Zero.
It's going to be replacing the content of r, and then you're going to see that. What does it happen now if I execute this line?
It gets from 0.
So the point here is that everything gets 0. So this is an important difference that it happens. So if you're familiar with MATLAB, for example, every time you copy things, there are memory copies. Here you have to be very, very careful because in Torch by default there is basically sharing pointers to the same allocated memory. So R and T share the same storage space, so the same space on the RAM on your memory system. And then they have simply, for example, different views, different kind of shapes, or anything you may like. Okay. So by default, whenever you create new tensors from other tensors, you're just reusing anything that was there before, and anything you're going to be doing to the other tensor is going to be reflected in the other one. So, for example, if you're going to be loading some data from NumPy and you import it inside Torch, if you change stuff in Torch, also the NumPy array are going to be changed. And the same way, if you change things in the NumPy, you get also the Torch stuff changed. There's a question over there, I think.
On resize, you have to keep the same number of dimensions, correct?
That is correct.
Okay.
Because I just changed the shape, right, of this tensor. All right, so here we have seen that by zeroing a tensor that has been created from my previous tensor creates this kind of problems. I call them problems because sometimes you forget about this. That's why it's very important, and I'd like to highlight this is very important to make a clone anytime you'd like to store some intermediate result. If you don't do that, maybe you make a dictionary or whatever, a list of several tensors during a process, and then at the end you check all those tensors, all of them are the same tensor. So if you'd like to spawn out like a new tensor, you need to use the clone command. So here I have S, which is a clone of R. Now let's fill S with ones, okay? So now my S is going to be a tensor, the same size of the R, but now filled with all ones. If I actually execute this line here, I'm expecting to get all previous zeros we have seen before, because we made a clone. Okay? So everything, there is a memory copy here, and this implies there is some, time spent over the memory copying part. So that's why the memory copy is not default, because we always want to minimize the time spent during computations, and if you have memory copies everywhere, things get very, very slow. All right, so far, everyone is up to speed? Mm-hmm. Did I lose anyone? No? Okay. So let's keep going. Vectors. What are vectors? They are simply 1D tensors. We have also scalars. Damn it, I didn't put it here. Okay, let's go vectors. So here, in this case, my vector v is a tensor of which content is 1, 2, 3, and 4. So what is the dimension and what is the size of the first dimension? Who can guess? How many dimensions this tensor have? It just has one dimension, and the size of the specific dimension is 4, because here you can see those 4 elements. So here, reiterating a vector, it's simply a one-dimensional tensor. All right, so let's go on. So here we have, for example, W, which is my weight matrix, my weight vector, which is 1, 0, 2, 0. If I'd like to perform a element-wise multiplication, I just use this simple star. And if I type V star W, I'm gonna get simply 1, 0, and 3 times 2, which is 6, and 0 again. Right? So this is element-wise multiplication. It's very commonly used for masking, for example, input. Instead, if I'd like to perform a scalar product, wherever I'm basically computing the projection of one vector towards the other vector, I just use the add operator. And so the add operator, if I execute this one, it gives me a scalar tensor of dimension of value 7. And this one is 1 times 1 plus 3 times 2, right? So this is 1 plus 6. And this is the scalar product of these two vectors we have seen before. All right? Good? Nice.
Why do you have a semicolon in a? So, for example, in the V, is that a syntax?
Okay, so the semicolon here allows me to write 2 different Python instructions on the same line. So I could have simply press return and have 2 lines, but then it takes more space. So sometimes I prefer to just put in 1 line. All right, so let's go on here, and I'm gonna be showing you a random vector of size 5. So the dimension is 1, size is of the first dimension is 5. If I press this one, we are gonna see that the first number can be addressed by putting square brackets and number 0, and the last number can be extracted by putting -1 in the square brackets. All right, if I'd like to extract a subtensor, I can just say from which element, for example, element number 1, which is 7, up to element number 2, which is number 5. And then I have to put a +1 because Python just considers the last element excluded. And so this one is the subtensor 7 and 5. Again, it's very important here. If I'm going to be zeroing this guy here, you're going to be basically writing a 0 in this location here. Okay? No, there is no memory copy happening here.
Excuse me, what was +1?
Because Python considers the first element included, the last element excluded. So here I'd like to be going from...
Yeah, I understand. I thought there was something wrong.
Okay, no, that was it.
Thank you.
Sure. All right, so let's get back to my vector V. My vector V was the 1, 2, 3, 4 one-dimensional tensor. I can actually reproduce the same result by using the A range, going from 1 to 4 plus 1. So this is another way of writing a simple range, tensor range. I can compute the power on this guy by simply using v.pow. Okay, so v.pow rise every element of my vector to the power of 2. Again, if I print v, we see here that v is the same, right? We didn't change the content of v. In order to change the content of v and rise every element of v to the square, I mean to the number 2, we just have to use the underscore here. So if I execute this line here, we're gonna see 1, 4, 9, 16, and the same here we're gonna see 1, 4, 9, 16. So in this case we have replaced the content. Again, underscore after the name, you're gonna be doing some destructive operation. Right? Good? All right. Next one, matrices. So what are those guys? They are simply two-dimensional tensors. I can, for example, define them in this way by writing torch.tensor, and then I just provide two lists of numbers. And here I show you this guy. So if I ask for dimensions, how many dimensions has this tensor? Number 2, right? Because there are 2 dimensions. It's a matrix. If I show you here the size of these 2 guys, first one is 2, so there are 2 rows, there are 4 columns, and overall the sizes are 2 and 4. how many elements does it have? If I ask number of elements, we see there are 8 elements. So again, this matrix can be also thought as a point in an 8-dimensional space. And again, here you have a sequence of a list of how you can address different elements. For example, you can extract one specific scalar, or you can extract the same exact scalar. You can extract one column, or you can actually preserve the dimensionality. So I would say, yeah, they are not too important, but at least here you have the whole combination. So here you extract a row, and here you extract one-dimensional tensor. So in this case here, when we use the square bracket around the number, you extract actually a still 2-dimensional element from a 2-dimensional tensor. Otherwise, you extract a subdimension. All right, almost finished. So in here, I just create my V range, going from 1 to 4, and I multiply it with a matrix. So M was this matrix, right? I show you here, the 2, 5, 3, 7, and 4, 2, 1, 9. And here I perform the matrix times vector multiplication using the at operator. And here we get the 49, 47, which is simply the scalar product of the first row and the vector, and the second row and the vector. Okay? That's classical stuff. Then there are all operations defined as well on matrices, like summation, subtraction, multiplication, element-wise multiplication, and element-wise division. And then we have also the transposition that can be performed by typing .t, or the same way as fully writing the transpose name.
And I'm guessing there is not element-wise, but normal multiplication.
Say again?
There must be matrix multiplication too, right?
But this was the matrix operation, right?
I thought you said element-wise multiplication.
The one with the at is the matrix multiplication. Where is it? Sorry. Here. M times V, right? So I show
M is
you.
multiplying by vector.
Yes, M is a matrix, and V is a vector.
Yes.
And here I have matrix times vector.
So you can put that.
And here I show you the result, 49 and 47, is the result of the scalar product between the first row and the vector, and the second row and the vector. Does it make sense? All right, sweet. All right, so constructor. There are many ways of creating those guys. And for example, you can use the range, you can use linspace, zeros, 1, the I identity, and you can also create random. You can create random tensors by using rand_n for normal random data, and rand for just the uniform. The different tensors also carry a specific type. They may be float, they may be double, they may be long, they may be integers and whatnot. So you can cast different types of tensors. As we have seen before, we can type torch.star tensor to have the full list of this kind of format. So this is like the different format of the underlying memory used by the different tensors. I'll show you how to cast different things, which is kind of straightforward. So here I show you my matrix M, and I can cast it as double. So in this case, it's going to be a float 64, whereas before the matrix was simply a float 32. Underneath here, I can just cast it as byte. So here, every time I'm casting the tensor in a different format, I'm going to actually make a memory copy, of course, because we have different sizes of memory allocations.
Sorry, if it's, for example, not in integer, so it automatically will round, and if you will cast back, you will lose this, or how it will work?
Yes, I don't think it's not going to be a rounding. It's going to be a ceiling, usually, when you have casting. It's like C, if you cast in C language, right?
So if you cast, you cannot cast it like that in C, right? Because if you have a double, you cannot cast it to integer. You need either to round or cut or you. So to understand what I'm saying.
If you cast a double in int
what you will get?
in C, you get simply the ceiling sail.
Okay, it's okay. It's lower.
Yes, that is correct. Sorry, my bad. You get the floor. Yeah, you get the floor whenever you're casting. Yeah. All right. So one nice thing is that if you have a CUDA device, basically if you have a GPU on your machine, you can also do very interesting things. And for example, you can cast a tensor to CUDA, which means you're actually copying your tensor from your RAM, your machine, to the memory on the device, on the actual GPU. Okay. So in my case, I don't have the CUDA, so I cannot run this line. But otherwise, if I would have a GPU, I would be able to basically move the tensor from my own RAM to the graphic card.
So if you run in your case, what we will get?
So in here, in this case, since we wrote that device is going to be CUDA if there is CUDA. Otherwise, in this case, M is simply sent to CPU. So this one does nothing.
So I cannot check do I have CUDA or not, right?
You can type this line, and you're going to be able to see whether you have CUDA on your machine or not.
If you're working on a Jupyter Lab, you will have CUDA. And
on my computer.
yeah, then
It's
you can always just type
unlikely that
NVIDIA
you-
SMI.
All right, so the other nice part is that you can go back and forth between NumPy and Torch without any issue. So in this case here, I'd like to have my M tensor in a NumPy format. So I can simply say m.numpy, and I'm going to be having my metrics converted into a NumPy array. So if I execute this line, we see that this guy now is a NumPy element. So you can go back and forth between Torch and NumPy without any memory copying, which is a very good thing. For example, here in my M NumPy, I set the element 0, 0 to -1, okay? So if I execute this line, you can see the first element over here, it's set to -1. Now if I execute M, which is my tensor in Torch, you're gonna be automatically seeing the first element is set to -1, okay? So there is no memory copying, once again, unless you cast things, unless you copy them from CPU to GPU, there are no memory copies. Finally, here I'm gonna say n_numpy equal a range from NumPy, and then I say Torch initialize basically from NumPy, and then I print both of them. And here doesn't work because I haven't specified NumPy. So I go above, I do import NumPy as NumPy, and then I can execute this line. And here you can see that my first element is my NumPy array here, and then I created the tensor from the NumPy. So this is very, 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 very useful. Whenever you have a data loader you have implemented for your whatever application, in NumPy or TensorFlow or whatever, you can simply reuse it in Torch, and you can simply convert NumPy's arrays into Torch tensors without any issue. The point is that whenever you are in Torch, you can also use those tensors on the GPU in order to perform accelerated computations.
So NumPy has stored the tensors too?
No, NumPy has tensors too, but they don't run on the CPU, on the GPU, right? Yeah.
It's worth pointing out that just about everything that you've just shown are NumPy features, and it sounds like Torch is for this part so far is a thin wrapper around NumPy with different names and such. A lot of the names are different.
Yes. So it's not a wrapper on NumPy, although the names are. Now they are trying to actually make the names to be very similar, but those things are actually implemented with different libraries.
Okay.
So but yes, they try to make it look like as NumPy as close as possible. But yes.
I'm getting error on this section, right?
Are we done in 5 minutes? 3 minutes? Okay. All right. Yes. All right. Yes. All right. So the last few lines, and we are done here. So in this case, I have n, which is my tensor, and I multiply with the underscore by 2. So what's going to happen here? My tensor was the tensor from 0 to 4, and I multiply by 2. It's going to be from, of course, 0 to 8, but also I'm going to be replacing the content of the n.np. Do you understand these two lines? What's happening? Yes? Okay, very well. So here you can see the content of the NumPy array has been replaced by performing an operation on the tensor. Finally, you can concatenate stuff together by just using torch.cat. So here I create these two guys, which are two different row vectors. And here, for example, I can concatenate those two on the 0 dimension. And on this line here, I can concatenate them on the other direction. You can find more information if you go on the PyTorch page, and you can click here on the link. Okay. So here you have the full description of all the API about tensors. And this was simply a quick primer on tensor. Stay tuned for listening about the next things. If there are no other questions, I see you after the break.